All right, welcome to the final talk of this morning. We have Indira Chatterji from Nice, and she'll be telling us about linear groups containing SL3Z.
All right, thank you very much. Thank you very much to the organizers. I love being here in Cambridge. Yeah, so before I start, I have two announcements. One, if any of you is going to the JMM in the US in January, or if you know somebody who's going to the JMM and would like to participate to a theater project that's going to be shown for the first evening of the JMM, please contact me. There's still a few opportunities to participate in this project. If you want to know what it is, you can go to my webpage and you find the project is called Methopoly. And you're welcome to check it out, to read the play, to add your own scenes and your own experiences. Right. So the other comments, the other advertisements that I have is that there is a special semester organized by LODA Institute next academic year on math related to that with a bunch of... And if you have questions, you should ask Mahan, who's here. He is the big boss of the semester. I encourage you to ask him. It should be fun. And what else did I want to say? Yeah, all this flying is very bad for the environment. We know that. And but we still do. And I flew here, actually. I tried for the past 10 years. I actually didn't fly much within Europe. It was a lot of fun. It was a lot of fun. It basically sent broke everybody who wanted to pay for my travel, because if I were to take the train to come here, it's roughly 7 times more expensive than the flight I took. And so, of course, you know, feeling a little bad, I thought maybe I should compensate my carbon footprint. So try to estimate your carbon footprints. You go online and you have a bunch of stuff. It turns out, if you do several weeks, you see very quickly, as a mathematician, you would like to know where the number come from. Well, if you really want to know where those numbers come from, you can go on MedPage. There is a short article explaining how you actually compute carbon footprints. But for the flight I took to come here, I wanted to know what is my carbon footprint, knowing that, you know, once as a mathematician, once you think about it a little bit, you know that whatever you're going to find online is highly unreliable. And it was actually the dispute between Greenpeace and Total Energies. But anyway, so what you can do, and what I encourage you to do next time you fly, is go to the cockpit and ask the pilots how many tons of kerosene we used on that flight. Because those numbers are very hard to find on the internet. But if you walk to the cockpit, he can look at the gauge and he will tell you. So just as an information, on my flight here, we use 3.8 tons of kerosene. And 3.8 tons of kerosene, if you do the computation, because you burn it, it takes some oxygen to become CO2. It's 14 tons of CO2. Divide by the number of passengers. I mean, of course, the plane would have flown even if I wasn't in it. But you divide by the number of passengers, you get something like 70 kg of CO2 for me, attributed to me. And if you go to the calculator, you see everywhere from 80 to much more. And the reason is, when you burn the kerosene, you're responsible for what you burn, but you're also theoretically responsible for what has been burned for the extraction. So in fact, the footprint, the 14,000 tons that this plane flew is an underestimation, because it's just the kerosene. It's not what you had to use to extract the kerosene to build the plane. Anyway, I'm very interested by those numbers. Next time you fly, if you ask how much kerosene you actually burned and send me the number, I would be very grateful. So now I'm going to do some exciting math. So I forgot the title, but the title was a Norris question. So Nori's question is the following. It's a question from 1983. The question is the following. You take gamma, a subgroup of G, and G is going to be a semi-simple Lie group. And gamma is Zariski dense and discrete subgroup. And then you take H, which is a closed subgroup. And it's also a semi-simple Lie subgroup. Later, I would want him to have higher rank, but for the moment, nothing about the rank. And the question is, if delta, which is equal to H intersect gamma, is a lattice, when does that force to be a lattice, when that force gamma to be a lattice? So here's the picture I have in mind. This is G. You have some H in here. Here you have a discrete Zariski dense subgroup, gamma. And here you know that it intersects in a lattice. When can you say that gamma was a lattice to begin with? Right. So the plan for my talk is to discuss all the definition, to give a status of what we know, and a sketch of proof. And before I go any further, this is joint work with T and Venkataramana. And it's actually a joint work that we posted on the archive on 2009, and that didn't get published and then for a long time, and it just got accepted, and it's galley proof, so it's going to be published. Right. But I think it aged particularly well. So I think that I think it aged really well. So that's why I decided that I'd like to. Also, I've been working on it, so but I might as well talk about it. Okay. Right. So I guess let's go. The plan. So in the joint work, what we actually do is we prove the following theorem. I'm not putting a date to the theorem. What we show is that in this case, if you have, if all your semi-simple groups are SLN R, and here you have SL3R in the top left corner. That's important. So if you have SLN here and you have SL3 in the top left corner, and if you have gamma in SLNR, which is discrete Zariski dense, and if the intersection here is SL3Z, so right. So if gamma intersects SL3R in SL3Z, so the wiggles, it's going to be commensurable, so up to a finite index common subgroup, and I never really know which way it goes, but yeah, let's just ignore the finite subgroup and the up to. So this is my wiggle. Maybe I should put two wiggles. I don't know. Then gamma is SL and Z. And, right. Okay. Okay. All right, so before I go any further, one problem that I've had on the back of my mind for probably too long is the following. For gamma is equal to SL and Z, show that the K-theory of L1 gamma is isomorphic to the K-theory of the reduced C star gamma. I'm just mentioning it because we talk about those C star. I mean, there is a C star audience, kind of. There's some kind of operator audience here. Anyway, so that's the question on the back of my mind. This is like a very important, it's very related to a very important open question that's been open for, I don't know, years and years. And no breakthrough, and yeah, nothing moved much for the past 30 years. There's a convoluted argument using Baum-Kohn conjecture that shows that this is going to be true for co-compact lattices in SL3R. But that's basically it. And with the recent results on that question, one question I had in mind is that even though you can't prove it for SL and Z, would we be able to prove it if we knew it for SL3Z? So that's the back of my mind. Anyway, if you're interested in K-theory, you can talk to me later. But there's going to be absolutely no K-theory or reduced C-star algebras or L1 in my talk today. Okay, right. So Norris question. So right. So it's about semi-simple algebraic groups. To me, so the definitions. So I'm not going to define semi-simple algebraic group, but just tell you that for me, it's just SLNR, or SLNR cross SLNR. So for today, you can just think of G is equal to G1 to Gn, and the GIs are, there's a list. So my favorite one is, I mean, it's not really my favorite, but it's the easiest one to define this. There's SLNR, SON1. There's a few more, there's a list. Anyway, so that's the list, but really, for the purpose of that work, if you understand the SLNR, the rest is hard work, or more hard work, yeah, more work.
So is this specifically SL3Z that you're talking about, or is this more generally a non-uniform lattice?
It's open for non-uniform lattices, and uniform lattices. Here?
The generality of your theorem?
No, you don't need non-uniform lattices or uniform lattices, just a lattice is fine, yeah. Yeah. Norris question, well, Norris question is really a question, and my collaborator insisted that it is a question and that Norrie doesn't have a guess and doesn't want us to assume that he has a guess. So no guess. It's really a question, but the question is open. Okay, so oh yeah. So what else do we need? Yeah, what else do we need? Well, we have Zariski dense. So Zariski dense is really for a subgroup in an algebraic group. So the group is defined by polynomials, and so Zariski dense, if you have two topologies on GL and R, you can either think of it as a subset of Rn squared when you have some topology. But you have another topology, which is the risky topology, which will tell you that a subset A in GL and R is closed if A is given as the set of zeros of polynomials, finitely many polynomials. So the basic example is SLNR, which is given as the set of matrices such that the determinant -1 is equal to 0, so that's a nice zero for polynomial. And in an SL and Z in here, so this is going to be Zariski closed, and SL and Z in here is not Zariski closed, but Zariski dense, because when you take all the polynomials, you end up with SL and R. Okay, and yeah, so Zariski dense, it means that the Zariski closure is the whole thing. Okay, and the basic example is in R, finitely many points are Zariski closed, but infinitely many points is Zariski dense because the only polynomial that has a zero is the zero polynomial. Okay, right. So Zariski density for me, intuitively, it means that the group kind of algebraically goes everywhere in the ambient group, even though goes everywhere maybe doesn't mean much, but yeah. To me, that intuitively, or geometrically, this is what I want to have in mind, is that the group goes algebraically in every possible direction. And there was some early examples of Breuil, Long and Reed, Thistlethwaite. I'm not putting the dates here. When was it your PhD or after? I'm not putting the date. Alan just told me, are you giving the talk on that old result of yours? I should have said, I'm going to cite much older results of yours. Anyway, so what did they do? So they managed to have F2 surface groups in SL and Z, Zariski dense in SL and R, and right. Back then it was a big thing. I mean, at least in my mind, I was a student. I didn't know anything, but it looks like a big thing, and now it looks much less surprising because those things are kind of have many different directions and they're kind of floppy, so it's less surprising that you could put them everywhere in SL and R. But you know, that's how math goes. Yeah.
I don't recognize.
You don't recognize your work?
No. It's okay because you didn't spell my name properly.
All right. I'm not very precise with the attribution. All those people have jobs, so maybe it's not that bad. Okay. Right. So I didn't. Okay. What did I say? 40. That's how much time I have left, or minus 10. Okay. Okay. Right. So more examples. Oh yeah. So the rank. I mean, we've seen that in many talks. The rank is the dimension of the largest flat. And a lattice is a discrete subgroup of finite covolume. So finite covolume, it could be co-compact or non-co-compact. And, right. So the examples are SLNZ in SLNR. A nicer one is SL2Z adjoint root 2 that you can put in SL2R cross SL2R. And those are non-co-compact. If you want co-compact ones, then you have to work quite a bit more. But they exist, and there's a lot of them. So what do you know? What do we know? I promise you what we know. Right. So what do we know? What do we know about the subject? So one thing that we know, and it's very easy to do, is you take H3. So this is the argument by Fricke-Klein. You take H3, you take a copy of H2 in it, and here you have a surface subgroup in H2, and so the Lie group is going to be, so the ambient group is SO31 and SO21, and then you take a hyperbolic isometry, gamma plus, gamma minus, and so gamma plus and here you take delta, which is a surface group, sitting in H2 as a co-compact lattice, and well, and that's it. You do this, and that's, if you do your thing well, this is a discrete subgroup. And it's Zariski dense because the boundary of it is going to be dense in the big boundary. And it cannot be a lattice for many reasons. For instance, it doesn't have the right boundary, or later maybe it doesn't have the right spectral gap. I don't know. Well, that's for later. But yeah, okay. So, so not a lattice. So this is Fricke-Klein. There is another result by Johnson and Milson, 1984. So what they do, so here it's, now this time is in SLNR. So what they do is that they have SON-21 in SLNR. And so this is SLNR. By the way, SLNR doesn't really look like this, but that's the best we can do. In fact, SLNR, you decompose it as, we decompose it as KAN. So this is the, this I think it is Iwasawa decomposition. And so this is SON, the maximal compact group. So this would really look a little bit more like this. Even though that's not true, it has all the topologies in there. So maybe, okay. Yeah, so A is diagonal matrix, and this is where you see the rank, because it's going to be this R to the n-1, since there is the determinant. And yeah, and N is this nilpotent subgroup. There is another decomposition. Well, this one I think doesn't give me the best geometric intuition. I think the geometric intuition I prefer is from SLNR being KAK, which is called Cartan decomposition. And that way you can get that way you can get the symmetric space, which is G mod K. And so you can think of the G mod K as Ka in a sense. And for SL3, it becomes easier because then the A are copies of R2, and are copies of R2 that you move with SO3. And so you can start to see your copies of R2 that you move with SO3, and that will kind of travel close together and suddenly branch exponentially fast. And the way they branch is kind of in the same way as the building actually branches for real in SL3QP. But that's, that's for the geometric intuition that I have as a bunch of flats. Well, it's a fuzzy version of a building, I guess. But it's mainly just more an intuition. So anyway, so here you have SL and R, and you have this copy of SO n-2 one, which let's say sits somewhere here. SO n-2 1, that sits somewhere here, and they create gamma, a lattice in SO n-1 1, which contains SO n-2, which is Zariski dense.
Somewhere here, the SO n-2 1 is supposed to be inside SL n-1.
Maybe. Well, if it's in SLN-1, it's going to be... No, I think it's really in SLN. They put it in SLN in such a way that... and they create a lattice in SON-2, which sits Zariski dense in SLN-R, but that intersect this copy of SON-2 in an actual lattice in SON-2. And gamma intersect SON-2 1 is a lattice in
the SON-2 is the block in SON-1 1, which is the standard representation in SLN.
I don't know. I'd imagine the standard representation. I don't know. No, I don't know. Let me just say that I don't know. Yeah. Okay. Okay. So already here we see a little bit of higher rank appearing because SLNR is higher rank, and we have this lattice which is rank 1 because SON-2 or SON-1 is a hyperbolic, is a rank 1 element. So what you get is a rank 1 lattice, and that extends in a lattice that sits in a Zariski dense way in SLNR. But it cannot be a lattice in SLNR because SLNR has rank 2 and the lattice is hyperbolic. And gamma is hyperbolic because, or if we say co-compact. Okay. All right. And right. Let me just mention if G is rank greater or equal to 2, then we had some other results when you have H and G, which are horospherical subgroup. And that's work by Hio, Yves Benoist, and Michael. And that's work that went from 1988 to 2018. Okay, and but the surprising result that came very recently is where will I put the surprising result? Here. Seriously?
There's.
Oh, okay.
On the left.
Okay. Yeah, I should have used the stick. So the surprising result came more recently, which is 2025. who showed that they find SLDZ free product F2 in SLNR. I think it's even in SLNZ, but it's not on my note. Anyway, discrete, Zariski dense, and that cannot be a lattice because a lattice will have property T. This doesn't have property T because it's a free product, so it cannot be a lattice. And right, and the way they find it is they take SLDZ and they make it act on S2RD, which is the symmetric real D cross D matrices. And they add some trivial piece, and they put that in SLNR. And so I tried to read their paper, but it's too long, and I'm not a very avid math reader. Sorry?
Is there any condition on D or just any?
Yes. No. That means that D. Yeah. So D. So because of that, you have that n has to be D times D plus 1 over 2. So that's you. This is the condition. This is the fourth condition in D. The relationship between n and D is this one. And the picture I have in mind from having looked at their paper and listened to their talks is that somehow this representation, see, when you put it in the left up left corner, it's kind of very reducible because you have your blocks that splits everything, and then I'll give you a sketch of the proof on how we do it. So if we know that it's in this corner, then we kind of spread everything on this lattice. We use this lattice to spread everywhere. But here this representation is going to be already kind of very spread out in the whole group. And so this is where you're going to find your SLDZ, and it's spread out enough that using convex projective geometry, they can find some elements to do a ping pong. They find a ping pong table.
So
Don't ask me any question because I'm really out of my depth here. Yeah.
As opposed to your work with Venkata Ramana, this SLD representation inside SLN is irreducible?
Yeah, yeah. And so this is maybe, that kind of explains how the paper took so long to get published, because back then when we wrote it, we were very, I mean, at least I was very proud. It was a very hard problem. And then I'll tell you a word about the proof. Because so in fact, what we show is that Nora's question has yes answer if, well, of course, if the rank of G and the rank of H is greater or equal to 2. And this is always in the simple case. I don't want to think about the semi-simple case. And that's in this case. And if the dimension, for instance, if the dimension of H is greater than the dimension of K. In fact, yeah. So we show yes answer if the dimension, but the dimension of K is not that big.
K is the
maximum compact.
for G.
Yeah. K is the maximum compact for G. I mean, there's another. Yeah. Right. Okay. So to me, yeah, I thought it was very interesting to have this group here because it feels that when you have SL3R in the corner, you kind of froze everything else, and you can't find a ping pong table because whatever you do, you're going to the fact that you were in this flat will force you to go in all those directions you want to go, whereas the way they do this irreducible representation gives some more flexibility of what's left. And yeah, so back when we proved those results, people were kind of hinting that we should work more and get the general result because they thought that the answer would be yes all the time. We thought the answer would be yes all the time, but you know, I never really understood. I don't really understand this irreducible representation, to be honest. So we thought that the answer would be yes all the time, and that we should work more, and we didn't work more, so we didn't publish the paper. And of course now with this result, we don't need to work more because we know that the general answer is not going to be yes. So the sketch of the proof. The sketch of proof is, well, I'm going to give you the few results. Yeah, the first.
Could you raise that?
I can raise this one. There's nothing behind. Yeah. So the main theorem is if you have this, and all their simple groups, and then you have your decomposition as KAN, and you take and you call that P0. Then you have an action of H on G mod P0. Right, just because G is a subgroup. And if the isotropy, the stabilizer of a point, is positive dimensional, and non-co-compact, so that kind of means that H is large enough. Then, each time you take gamma discrete Zariski dense subgroup, such that gamma intersect H is a lattice, then gamma is super rigid. And super rigid means that gamma representation extends to the ambient group. Great.
I don't understand the relation between the assumption and the assumption is that there exists a point with isotropy which is
All point.
All point?
Well, yeah, all all points have positive dimensional non-co-compact isotropy for the action of H on G mod P, 0.
But H will have a closed orbit in G mod P. There will be a point where the
Wait.
So the isotropy in H, or
The stabilizer. So here, yeah, the stabilizer of a point. Yeah. All right. Let me think about your question. Okay, so this proof is an adaptation of Margulis superrigidity. You have a representation of gamma. You restrict it to a rational representation on delta, and then Furstenberg allows you to get allows you to get a map from G mod P0 to the probability measures, and the fact that its isotropy is big enough, you extend the whole representation. So once you've extended your representation, you use a result. You use a result by Venkataramana. Venkataramana tells you that if you have gamma in SLNR that is super rigid, then gamma is a subgroup of an arithmetic subgroup of and then once you have that, we take, so then this condition shows you that it works well for SL3 contained in the SL4. This condition on D and the, so using that, you have your discrete Zariski dense subgroup in SLNR, and using that, you start with SL3, and then you prove that the generic element of SL3 will conjugate SL3 in the upper half corner to SL4 in the upper half corner, and you keep going until you get to SLNZ. So basically, this is what you do. You take you take your generic element, and we show that you can take a generic element of gamma. Will conjugate this guy. It's always the same guy. It's always the same guy. 1 plus E13. That's the important element. And this will allow you to take your lattice here, using an element of gamma, get a lattice here, and then get a lattice here, and then you do your induction in that way. This is actually the most important element, I think, on the Earth. Right, and okay. Right. Oh yeah, the positive dimensional isotropy to get super rigidity. So here's how I see it. You use that. Here you're on. Here you're in G mod P, and so you have a slice where you can extend your representation, and then you keep looking at all the H orbits, and you extend everywhere, and in the end you have extended everywhere. This is like a really bad hand-wavy end of the proof. And I think I'm early, so, but anyway. I think everybody appreciates to finish early, so I'll stop here. Thank you very much.
Right. Questions for Indira?
Can you say more about it's super gloomy, but it's, see, you assume that the rank of H is at least 2, so you can extend it to H, right? I mean, that's the...
Yeah, you have a representation. You extend everything to H, and then you use the fact that when H acts on G mod P, it's so large that it kind of steps. You know, it takes so much space that you can extend the whole thing, but you can patch up the thing together. Yeah, yeah, that's the intuition. Although, then you have to write it. But to me, that's the intuition: is that when H is large enough, then you have this those pieces that you extend, and then by moving it around, you end up extending it everywhere.
Right.